There was a good question after class that I wanted to clarify. Feel free to ask during class if you want to. Which was, we had some kind of result that was like this. The performance of our learner using the Dagger algorithm was something within the epsilon u of the performance of the expert policy. And someone naturally asked, well, what pi do I mean when I say this j pi, right? Well, the answer is, if you remember when we ran this Dagger algorithm, what we proved is that as time got longer and longer, because the regret was getting, on average, was getting small, if you basically pick a random example policy, it's very likely to be consistent with its own distribution of states. Meaning, if you look at the states that it induces when you run that policy, it agrees with the expert a lot. Okay, which means there must be one policy in the group that agrees with the expert a lot. What I mean by the j pi is if you picked that policy. Okay, so it is worth noting it's not necessarily the case that when you run something like the Dagger algorithm that the last iteration is good. It actually could be in a no regret setting. No one promises you in a no regret setting that any given iteration is going to be good, right? So it's worth noting the last one is not necessarily special and it might not be good. The claim is just that there must be one policy such that this holds, right? And you can find that one by finding the policy that has on its own induced distribution. So if you look at the distribution of states it induces and you look at its agreement with the expert, it has the best agreement with the expert on its own distribution. Okay. Does that make sense? Okay.
So we do that by looking at a validation set or something?
Yeah, you would naturally look at a holdout set of, not the aggregated data holdout set, right? You look at the data, a holdout set of data of running that policy and seeing what the human, how often the human or whatever the expert is, agrees or disagrees on that holdout set. Right? In principle, if you could guarantee you weren't overfitting, you could do it on the training set too. Does that make sense? So just a point of clarification. And the point is actually, there always exists such a policy, but actually because the regret is going down, lots of policies actually have this property. Not necessarily the last one, but lots of them are going to have that property. Okay. Go back to that in a moment. Let's see. So today we're going to talk about approximate dynamic programming. So this is a follow-up really to Stephen's lecture on Bellman equations and dynamic programming. So approximate dynamic programming. The first thing I want to introduce, because we've already sort of discussed it in various forms, so I want to give a little formalization to it so we can talk about it, is the idea of access models to an MDP. So how can you interact with an MDP when you're trying to solve it? Okay, so I think the version that Stephen had in mind when he was talking about the Bellman equation and value iteration-like things was what I would call a full probabilistic description. Meaning, you have a complete description of what all the states are in the world. So you have a complete description of S, a complete description of all the actions in the world. Most significantly, you have a complete description of the probability of S prime given S and A. You have that as a closed form description. You can think of it in your head as a big table, right? There's a big table of what's the probability of ending up in any S prime given you were in S and you were in A. You have a complete description, there's the horizon length T, it's sort of obvious. And you also have a complete description of the cost function or reward function, so cost of S and A. I'm really bad at keeping track of the difference between cost and reward. And so all of the bounds I will have, I will not even remember whether it was cost or reward. They all end up being flipped upside down. It's worth noting that you could have cost or reward, and they're just logically the inverse of each other, right? The negative of each other, right? So cost is negative reward. Okay? And it just changes whether you are trying to min or max things. Right? Unfortunately, both appear very commonly in the literature. So you have a complete description of all of these things. I don't think there's anything else that you need a complete description of. And you're gonna run something like this value iteration algorithm Stephen talked about to try to get yourself an estimate of either V star or V star. What do I do if I have Q star? What is Q a function of again?
State an action.
State an action? Maybe time, if it's a finite horizon one. So it could be that this is Q star T of S and A. If I have this thing, what policy would I execute? What's the,
Maximum over the actions.
assuming I like rewards, yes. Yep. So the policy that I would execute pi star equals argmax over A with U star. Okay. What about V star? What's the interpretation of V star? Trying to remember how much Stephen talked about V star versus Q star. Both. What if I give you V star but I don't give you Q star? What do you do? If you have a full probabilistic description.
Use the transition count to see.
Yeah, you're gonna have to. Good. Okay. So what will my pi star be if I only have access to V star?
Max reward plus expected value of V star over states.
Argmax for A of the reward T S A. Okay. Plus. Go ahead.
Expected value of V star, like over S prime.
Over S prime, where this expectation is under P of S prime given S and A. Right? So A is being bound here. I'll often just make the cost of rewards a function of state. Turns out without loss of generality, you can consider it just a function of state. Just like without loss of generality, you can consider it a deterministic function, which I'm ignoring right now. You could also have the rewards be stochastic. They could be randomized. It doesn't actually change anything. You basically just end up getting the average of the rewards. Okay, so this is annoying, right? This version is annoying. Why is this annoying? It's not annoying if I have this full closed form description, but why would it be annoying if I didn't have a full closed form description? This one's easy, right? Think about it as a giant table. I have a giant table of S and A, and all I have to do is plug in my S and find the A that optimizes it. Okay. This one, I'm basically doing one step forward search, and I'm computing this expectation. So I have to actually have this in some form. Right? Closed form is the obvious one to be able to compute this expectation. Okay, so I have to do like one step look ahead when I have just the V function. That's the advantage of the Q function. It's a bigger table, right, because it's Q of S and A. However, I don't have to do forward look ahead to figure out the best action. Okay, so that's a full probabilistic description. And I'm going to give these to you in order of power, so to speak, in the sense that each model will be able to simulate the thing beneath it, but not necessarily vice versa. Okay, so this is like the most information you could have. You just have the MDP completely in a giant table. The next model that you consider is called sometimes a deterministic simulative model. Okay, the simplest version of this is you just have a function f of x and a that maps deterministically to x prime. changing from S to X, another bad habit. So in controls, it's always X, and in reinforcement learning, at least the psychology side, it's always S, and computer science, it could be either. Okay, that's one version of the deterministic simulated model. So that is, it's literally deterministic, right? You have a function you can call at a state and plug in an action, and you get an S prime. Okay, there's a generalization of this idea, which is, think about it as you have a stochastic model, okay? And the simplest version of a stochastic model is I'm allowed to draw a sample, right? So I can draw a sample from my simulator and say I'm in state S, I choose action A, I draw a sample, I get an S prime. Okay. That's very natural. In fact, that's what we're gonna talk about next. But there's a more sophisticated version where I can basically reset the random number generator and I can always get the same sample, right? So I could put you back to the same state with the same random seed and generate the same sample. And sometimes there's an advantage to that because you can often reduce the noise, reduce the variance by being able to fix the random seed and compare things. So the deterministic simulated model that I have in mind here is that you have access to a thing that will sample S prime from P of S and A, and it will let you fix, I'm gonna call it omega, a random seed. You can plug in the random seed. So in fact, you can reuse the random seed if you want. Okay. I don't think it will ever matter in this class that we have the deterministic simulated model versus not, but it's sometimes useful. Okay, then we have what's called the generative model. Which is I can sample S prime from any S and A, but I can't reset the random number generator. Okay, so you would think, like, you would actually think normally in a simulation, this would be really easy. It's surprising how often it's very hard to get the exact random seed back in a simulator, surprisingly. It's surprisingly hard in many simulators to actually get it back to the same state. It should be trivial, right? Because the simulation should be deterministic. But as Gokul and many others can tell you, it's surprisingly difficult in many simulators to actually get it back to the same state so that you can draw samples that are independent draws from that distribution. Nevertheless, in principle, it should always be possible in a simulator that I can put you in a state. This is not necessarily true in, for instance, lots of real world problems, right? I can't just like arbitrarily place robot in some state in the world, right? And see what happens next. Okay, if you think about like a robot doing some kind of dynamic action, like jumping through the air, it's very hard to put it in the state like in the middle of the air, right? Okay, so these are great models of simulations, but they're not always great models of a non-simulation, the real world. So it depends. Okay, the next model is called the reset model. Sometimes it's called the trace model too, which will make it confusing with the next one. Okay, what we can do in this model is I can start you off at S0 and I can execute any policy you'd like and I can draw a trace of states. So I can start out at some S0 or some distribution P of S0, one of these two. Okay, I can start out in either one of these things, and then I can just draw, taking a policy in, so let's call it trace of pi, will give me back a sequence, S0, A0, R0, S1, A1, R1, and so on and so forth, up to time t, whatever our horizon length is. Okay. I can call this function and it will give me back trace, right? That's a pretty reasonable model of a lot of real world problems that you can like put the robot in some initial configuration, maybe not precisely, maybe you put it in some distribution of initial configuration states, and then you can run the robot through the world, okay? It can be hard to put it in an arbitrary state, but you can put it in that state. Okay, and then there's the model we won't talk about at all, which is the hardest one, which is sometimes called the trace or single trace, which is the more accurate version. Kind of single trace model. This is super hard. This is the model where essentially T is infinity, and you just run forever in one single ongoing trace. Right? So you can never reset to anything, and you just have to see how well you can do in this single trace. Okay. There are some algorithms that work in this setting, which is kind of interesting. But I don't think we'll talk about any of these kind of single trace versions in the class. That's tough. Okay. So we're going to focus mostly in this class right now, today, on kind of this version as a weakening of the algorithm techniques we applied in this version. Okay. We're going to think about this kind of generative model version and ask what we can do. So probably the most straightforward thing we can do in approximating the algorithms that Stephen talked about is we can try to approximate the algorithm. Let's talk about approximating the Bellman equation. I'm going to try to approximate things like value or Q iteration. I was reminded, by the way, the reason for Q, I'd forgotten about this. So looking at notes again. Q is for quality. That was the reason for Q. But Q is pronounced action value. So Q, think action value function. Okay. As opposed to the value function. But the reason for Q is actually quality, if that helps you remember. Okay, so what we're going to do is First, we're going to remind ourselves what Q means. X, T. Okay, what does Q star XAT? What does it intuitively mean? And then the other thing we're going to want to talk about is Q pi XAT. Remind me what these things are.
Expected reward plus the Q function at SP.
Yeah, we're going to be able to define it. We're going to be able to write it recursively, as you just said. So I'll write that down. AT is going to be equal to, let's say, cost. Sorry about the x's. Can't help myself. At some point, you're just going to have to learn that when I say x, I mean s, or vice versa. Promise not to use them for anything else except for that. Plus, did you talk about discounting? Remind me.
No, all finite horizon.
I'll leave that for right now. Expectation. Prime, S, A. T plus 1. I made the rewards not a function of time to make it simpler. They could be, but it doesn't really change it for me. Okay, so this is recursive. I would not define this as a definition. I would define this as a theorem, right? This is true that the best reward, oops, and this better be solved. Before I say why this should intuitively be true, what is this thing supposed to be? If I do what? I start in state S at time t, and I do what?
Reaction, and then thereafter act optimally accordingly.
And thereafter act optimally, right? So I get the cost of S and A plus total future value of acting optimally. What's this one?
reaction A and follow pi thereafter.
CSA plus total future value of following pi. Following pi from then on, right? You can think about it as I deviate from pi potentially and choose action A, and then from then on I follow pi. Good, and so that means Q pi, SA, also CSA, plus what? What goes here?
That's all we'll go with the star.
Not quite, but close.
Well, you sample A prime from pi two.
Yeah. I'll just call it, to be lazy, assume it was deterministic. You are correct, if it was stochastic, you would sample A from pi. Good. Okay, so now what we're gonna do is we're going to try to take advantage of this recursive relationship. Okay. And we're going to compute these Q's backwards in time. But we're gonna do it from samples, which is a little different than and so let's talk about what's called fitted Q iteration. Okay, so we're gonna have a data set that this thing takes. So we've got a data set here where we've got states that are chosen, actions that are chosen, costs that come from being able to pull on the simulative model and say, hey, if I give you this state and action, what cost do you get? Right? That's one of the things I can ask the simulator, what cost do you get? And then I can call the simulator and get a sample SI prime. Okay? So I built this data set by starting with a bunch of states and actions. We'll talk about where you might want to pull these from to begin with, because there's a bunch of initial states and actions. Where do these come from? Okay? But I can put the simulator in S state SI. I can apply AI. I get my cost. I get my next state. That's the data set that you're thinking of as fixed for this purpose. Okay? For this algorithm's purpose, that is a fixed data set. If you'd like, you could also make these indexed by time as well, so you had different states at different times in the sample. I'm gonna ignore that detail, but you could add that if you want. Okay. And what we're gonna do is we're gonna say that Q, X, A, T is initialized to the 0 function. Okay. So that's for all X, for all A. Okay. And then we're gonna do for all T in -1, 2, time to 0, assuming that we start time at 0. That is the null set. Okay. And then I'm going to index into the data set itself. For all I, to find the input as SI AI. I'm gonna find the target as CI plus min A prime Q X, oops, X, S, S, I prime, A prime, T equals 1. So this is the target future reward I'm going to get. Okay. I'm gonna just add this to a data set. Union input comma target. So input output. Okay. And then I'm gonna do Q T is apply your favorite regression algorithm on DAT. And then we'll return Q, which is actually a set of Qs, right? It's kind of one Q for each time step. Okay. I'm gonna return that Q. Does that make sense? Okay, so what are we doing? We're stepping backwards through time, right? And the first thing we're doing is we're finding what, for a particular state action, what is an estimate of what the future total cost, the best possible future total cost is. It's easy at the last time step because this is just 0. So the total future cost is just the cost at that particular time step. Okay? Then I get an estimate of what the cost is. I hand this off to a regression algorithm. That regression algorithm is now able to take as input a state action pair, and it outputs its best estimate of the future gain. Okay? Does that make sense? Okay. And then I reuse the Q that I just learned to help me estimate one time step further back. Okay. So this is the regression version of the thing Stephen talked about. Okay. What's good and bad about this? So this is a really, really old idea. Some variant of this using things like splines goes back to at least the 60s, maybe even earlier. Really old idea. What's good, what's bad about this? Practically, there's lots of details that you might want to do. Like you might want to actually make the input features not the states themselves, but maybe features on the states if you have some additional knowledge about the problem, rather than kind of raw states. What are questions about this? I guess one question I have for you all is, how should I pick this data set? So this part I don't control, right? It just comes out of the simulation. The only thing I control in picking the data set is this one and this one, right? Intuitively, how should I pick these things? In the case that Stephen looked at, how are we picking them? How would you want to pick the states and actions in this data set? Why would you just pick one state and one action? Why would that not be a good idea?
T will never include like information for other state action pairs, so your Q value just won't learn those.
Yeah, it won't learn those at all, right? So in the case of the exact value iteration algorithm, we're basically doing this for all state actions, right? We're trying to hit every possible state action when we do this update. Okay? So kind of intuitively, what might I like to have these state actions be? I can't get all of them. You might think about it in your head as a continuous space, for instance. I can't hit all of them. What might I like to be true?
Can I get like a representative sample of all possible setting actions, like maybe binning the spaces
Yeah,
for each?
right. So one thing you could do, right, so intuitively, one thing you might like is to have a lot of coverage, right? Put state actions all over the place. It seems like at least a minimal requirement is you better put states and actions, you better put samples close to where good policies are ultimately going to go, which we're gonna talk about. That's a minimum, but that's probably not enough, okay? And the reason that's probably not enough, we'll talk about in a moment when we pull up the slides, is you're going to get misestimates in certain places, and you might misestimate those more positively, and that might actually lead the algorithm off. Okay, so in kind of ideal world, you'd sort of get samples basically everywhere. Right? Okay, the problem with that is that as our state dimension grows, it gets harder and harder to put states everywhere. Okay? Or as our action dimension grows, it gets harder and harder to put states everywhere. Okay, so Stephen talked about what happens if you run this algorithm exactly, right? So if you run this for all state actions, let's ignore the randomness of C in the next state, but you run this exactly, this will converge to the optimal Q star, right? It's actually giving you at each time step the optimal Q star, which is awesome. And then you have the best policy. What happens if you run this approximate version? So Stephen, can we pull up the examples?
What the source for these is?
Yes, they are from a paper, which is I think linked in the notes, by Justin Boyan and Andrew Moore, on issues with approximate dynamic programming and some proposed solutions.
Are we gonna be using any good proposed solutions?
No. No, we're not. We need to go off the light, Stephen, will we be able to see?
Should be, it will be turned on in a sec.
Okay.
Somehow I cannot find this screen.
Infinite Stephen recursion?
We've also seen the lag, where like each time he turns his head, like the one behind him takes a bit longer.
The biggest challenge is
Finding your cursor?
finding the mouse.
Does this control the light, Stephen, right here?
I think so. Cool.
Okay, so here's a very simple problem. So, it's a continuous grid world. Okay, so it's kind of one of the simplest problems you can think about. You can move on the cardinal axes, so you can move, there's 4 options. You move up, down, left, right. Okay. You want to get from this location up to the corner. The true value function, looks something like, well, you can see it actually. So here are iterations. It doesn't start from 0, which is kind of annoying. But what you see is, I don't remember what the reward function is here. It's probably a cost of 1 for every step. Right. So if you arrive at the goal, the cost is 0. Okay. So the Q function is pinned to 0 right here. Okay. If you do a discrete value iteration, meaning you make a grid of the states, okay? And you run this for every state in the grid, you run the backup for every state in the grid, what you'll see happen is the value will back away from the goal, and then it will flatten because you can't, at iteration 12, you can't have incurred more cost than 12, right? So if you don't get to the goal, it'll be 12, and if you do get to the goal, it'll be however many steps it takes to get to the goal, okay? And so as you run this, you'll see this go back. Ultimately, it just becomes a linear function backing away from the goal, okay? So, very simple thing. How do I scroll, Steve? Mouse, nice.
If you can find it now.
If I can find the mouse. It's on the wrong monitor. Oh, there, I think I got it.
Oh, you got it?
I got it. I got it. Okay. Whoa. So, now let's do the same thing, but let's do it with a function approximation. Okay. In particular, let's do it with quadratic regression. So, meaning we're doing linear regression, but on features that are the x's and products of the x's, okay? The two x dimensions and products of the two x dimensions, okay? And presumably a constant term, okay? Then, so why is that an interesting class? It's an interesting class because it actually includes the optimal answer, right? It is a larger class than what is included in the optimal answer. You see all kinds of interesting things, like, well, it's sort of like qualitatively okay at early steps. The scale's a little wrong, which is weird, right? But then it actually flips upside down at some point in the iteration process. So it's weirdly unstable, even though the optimal value function is actually included in this set. So that's a little worrisome about this algorithm. Good. Your mouse scrolling is backwards, Steve.
That's the default.
I know, it's wrong. I'm old enough that I remember when the default was the other way. Okay, let me show you another problem. This is kind of a fun one. It actually gives you a little bit of a flavor of what value functions look like. Okay, so this is called the car on the hill problem. There was a time when this was state of the art. Okay. The car on the hill is very simple. It has a position, the car has a position, and it has a velocity. Okay, so there's two variables that matter here. The actions that are available to the car are to accelerate forwards or to accelerate backwards. Okay? You cannot, I believe it's set up so that you cannot just start at the bottom and go straight up to the top. Okay? There are, it turns out, a million variants of this particular problem. So usually the acceleration is bounded, right? So you can't just go straight up to the top. Sometimes they just cost acceleration, et cetera. Okay, so what you have to do is some variant of like pull back, go backwards, and then accelerate up the hill, get to that point. Okay, that's the goal. And so we should be able to read that off from the plot. Okay, so where do we want to get to? We want to get to position is 0.5. I think there are fancy versions of this where you want to arrive at the goal at exactly zero velocity. And the faster you're going when you arrive at the goal, the worse it is. I think this is just the very simplest one. So we want to arrive at 0.5. If we're there, great. Okay. I think this is reward. I believe this version of the problem.
Restart.
What's
I
that?
guess this one include the velocity at the state. Oh, I see. Velocity is action. Okay, sorry.
No, velocity is state.
I see. So the state includes velocity.
The state includes the velocity.
So it's the fancy version.
Yes, because at this position, if we have,
Oh, so you can have negative velocity, you can have positive velocity.
trying to decide why negative velocity is okay.
Because it means you're slowing down.
Certainly means it means you're going backwards, right?
So you can fall back.
Velocity.
You just don't want to overshoot the cliff.
Yeah, so if you arrive at the goal and you're going forward, in fact, if you arrive at the goal anywhere, it's cheap, right? You've arrived at the goal, it's zero cost to go, okay? Anywhere along, oops, yes, anywhere along the 0.5, right? If you are almost at the goal and you're going not going with any velocity at all, you don't quite make it to the top, right? And then you go sliding back down. That's real bad. It's really expensive because it's gonna take you a long time to get back up, right? So you see, right, there's a discontinuity in the value function. Right at the velocity goes negative, it suddenly gets really expensive. Okay. And so what you're actually doing is in the space of this value function, the optimal policy is gonna do some kind of spiral like this. Okay, it's gonna spiral up to the goal, and what's actually happening is the car is going backwards and then up to the optimal shape. Okay, so that's what the value function looks like. So first off, it's noticeable that this is a super simple problem, and you note that the problem is a discontinuous value function, which is important, right? That you could have complicated behavior in the value function for very simple 2D, very easy to describe problem. Okay, so this problem you're not going to approximate with a linear or quadratic value function, so you might try something like a neural network. So this is a 2-layer. This is when deep was like 3 layers. Very exciting. So this is a deep neural network of depth 2. And we're running the Q iteration. I can't remember if it's Q iteration or value iteration, and you're just seeing the Q star with the optimal action or not. You see the same behavior either way. So you run this kind of algorithm. This is, think of this as Q of these 2 dimensions and the optimal action is what you're seeing. Plugging in the optimal action. You get some nice flavor of the answer in the beginning, right? So you're seeing the flavor of near the goal, you're getting kind of the right answer. And then you get some weird waves going on up here. And then really bizarre things happen. It just kind of goes to nonsense. And then in fact, it's like backwards, right? It's like actually saying it's cheaper to be down here, which doesn't make any sense at all, right? You're getting absolutely crazy values for training this neural network. Okay. Good. So that's.
Do you know how to collect the S? Do you just cover the whole space for?
How did they pick these initial samples?
Yeah.
Yeah, they had a random set of state action pairs to begin with.
Okay.
Yep, trying to just cover the state action pairs, which is fine here because it's only a 2D state space. And not like accelerate one way, decelerate the other way action space. So it's actually not that hard to do a reasonable job covering the space in this case. Okay. I think that's all I need to show from that. So you should be nervous when you start with something where the value function really is in the space of things you're considering and it still doesn't work, right? And you should be nervous when it can do really weird things like blow up. So let's try to get an intuition of why this goes wrong. How do I make the thing go up?
I'll do it.
Okay.
So for fitted queue iteration, are we interactively collecting samples or samples are given to us?
In this version, we are collecting samples fixed at the beginning. Yep. Right. So the question you ask is a great one. A very reasonable thing to do, and will generally improve performance, is you start with some initial batch of samples. You run this Q iteration thing I described. You get out a policy. You could then execute that policy in the simulator. You get a new batch of samples. You could put them together, right? And actually that will help a great deal in kind of stabilizing this thing, because at least you're getting samples in the places that your algorithm visits, which is sort of the heart of what's going on wrong in this particular problem. So let's see if I can kind of describe the basic challenge. And this happens with Q iteration or value iteration. Okay. There's two coupled things that are causing the problem here, that are causing this kind of bad divergence or oscillatory behavior of the value function. You can think about it as all being tied to this min operation, where we're minning over the next state. Let me try to give you an intuition of what goes wrong. There's a it's hard for me to draw multiple dimensions, I'm just gonna draw a value function. This is my state S, which we're thinking of as continuous. Okay, this is going to be V of S. Okay. Let's say there's some true value function unknown to us. And I don't know, it looks like that. Okay. Goes off. And up is good. So this is rewards not cost for a moment. Okay. I get a bunch of samples. So my samples are located in some part of the state. Maybe they're located right here. A couple samples, various other places. Again, think in particular, it's really hard for me to cover a high dimensional space, but it's hard for me to get dense samples everywhere. Okay. I fit my value function approximation to this function. What's probably true? Well, it depends. It could be my function approximator is just no good at all, in which case it just doesn't fit this very well, and then I'm in trouble. Okay. Let's assume it does a okay job in the statistical sense, meaning where my samples are good and dense, it's reasonably good. So, you know, it follows the general flavor of this thing. Okay. The errors get bigger where there's fewer samples. In fact, they can get really big where there are very few samples, because it doesn't have the, when you think about the like squared loss error, it doesn't have a great need to fix places, it doesn't have many samples. Obviously, in higher dimensions, this looks worse and worse, right? Because you get bigger and bigger gaps between your samples, and there's more and more space where you don't have it nailed down. Okay. If you are now backing up a time step, and you're deciding where should I try to move my robot, picture the S as the robot, and this is the value function that I have inferred for the next time step. If you had the choice, where would you try to move the robot?
The opposite direction of what should have optimal been, like in this case.
I'm gonna move it to wherever my function approximator says the value is high.
High, yeah, exactly.
So if there are places where the value function is an overestimate, right? So there's a big gap, right? And it looks like this is a really good place to end up, right? I'm actually gonna amplify the errors in my function approximator, right? Because what I'm going to do is at the next time step back, I'm gonna try to push probability mass out here. But actually that's where my function approximation is the worst, right? So anytime you do one of these backups and you're doing this min operation, right? Or in this case, it's the max operation, or I'm trying to find the best thing. I'm going to, if my errors happen to be high, if they were low, it wouldn't be a big deal, right? So if I like misestimated down, no big deal. The robot wouldn't want to go there. Okay, but if I misestimate high, what will happen is the time step back will want to push as many samples out here as possible. So anywhere I have a high error and the error is positive, in the sense that it looks better to end up at that location than it actually is, I will amplify the errors. If you think about this, this is very similar to the problem we talked about in imitation learning last time, right? This is a problem where the test distribution will not match the training distribution, right? I built the set of samples from somewhere. I didn't even specify where I built the set of samples from. Maybe just trying to get them kind of uniform over the space. The test distribution is actually going to put probability mass where my errors are highest. It's going to try to test on a distribution that's much harder than what I trained on, okay? In the same way that when I do the imitation learning problem, I train on the distribution of the expert demonstrator, but I test on my own distribution, right? So this general problem is called covariate shift. Covariate being statistics word for feature, so it's basically feature shift, right? I'm seeing a shift in the distribution of features at test time over training. Okay. That's the heart of why these algorithms perform very poorly, okay? And because, again, they just amplify any errors they make. Okay? And the only thing you can really do about it, so the reason The reason why the version that Stephen talked about works is it makes no errors, right? When it does a backup, it exactly gets the value right at the previous time step, and the error is just 0 at every step. So there's no errors to amplify. Okay. That's the heart of the reason that that particular version works. Okay, so what might you do to combat this? So the first thing we'll do to combat this, we're going to combat this in 2 ways. First, we're going to remove the min, okay? And then the min will show up in a secret way again, in the fact that we're going to try to estimate q pi instead of q star. Okay? Does that make sense? So this is, remind me, Stephen, you talked about policy iteration?
Yes.
Okay. So the game in policy iteration is I don't try to directly compute q star. I start with some pi. I compute q pi. I then modify my policy to be greedy with respect to q pi, and I do the whole thing again. Okay? Does that make sense? Okay. So the advantage of estimating q pi is I don't have this min operation in the middle of the q pi backup. So I don't have the amplification of errors in the q pi backup. I'm not actively trying to exploit errors in my value function approximation. Still get errors, they can still compound over time, but at least I'm not like actively exploiting them. Where is the problem gonna show up in policy iteration?
Again, the same minimizing step where we can take, where the minimizer action could be out of distribution.
Right. So what's gonna happen, let's look at a modified version of this. So let's modify this to just the evaluation step, which is gonna be pretty easy. So we'll do a modified version of fitted Q iteration, where I just call this pi, pi. A prime comes from pi of s a t plus 1 rather than a min. Does that make sense? So I've just taken the thing we just described before, and I've changed it so that instead of sticking that min in there, it sticks in the action, which is the action chosen by the policy pi. Okay. So now what I'm finding is not q star, but q pi, the value of the policy pi that I'm executing. Okay, this is actually not terribly unstable. Like, it can have problems, but it's not terribly unstable. Okay, the question is, now what do I do? What's the next step? Once I have q pi, what do I do in policy iteration?
Policy improvement.
I gotta get on policy improvement. Good. Policy improvement looks like what? What do I do? What's my next policy? This takes in q pi, right, for each time step, and what does it return? How does it compute the next policy? What was it? Yeah. So pi new, the next version, right, equals, and this is a function of s. Argmax, q pi. Okay. So if your q is a function approximator, you just wrap your function approximator in a thing that looks over the actions and picks the best one. Okay. I'm just gonna have the exact same problem again, right? Because, yeah, this thing was stable at getting q pi, but the policy improvement operator is going to push all the probability mass where q pi happens to overestimate, right? Q pi is an overestimate. Okay, so we'll talk more about it in a second because we're going to go to the kind of second approach, which is the more radical approach to fixing this problem. How might you mitigate this? This thing, reasonably stable. This thing, really not stable. What might you do instead? Okay, good. What would you regularize to? Where is this thing a good estimate?
The last state, at least. I mean, actually, no.
Some kind of KL divergence for that state between this, between this improved policy and the current
And the current
current
policy.
policy.
Yep. So a very natural thing is to say, I'm going to not return the argmax policy, but I'm going to interpolate between the argmax policy and my current policy. Okay. So there are many ways to interpolate. One that we'll see in a bit is make your policy stochastic, okay, so that at every state it chooses a distribution over actions. Okay, and then I'm going to write something that looks like nonsense, but I'll explain what it means, which is pi prime of ST is alpha times pi. I have to now take pi into this thing. Times pi of ST. Oops. More natural to make this 1 minus alpha, at least in my head. Plus alpha of this thing. Pi, let's call it proposed. This is the proposed improvement. Pi proposed. Okay. This doesn't type check because what does it mean to like alpha and 1 minus alpha policies, right? All I mean by this is flip a coin, right, or flip a random number generator. With 1 minus alpha probability, choose the old policy. With alpha probability, choose the new proposed policy. This limits the amount of damage you can do and how much you can shift your probability mass, right? In fact, if you think about this alpha as being something like, think about it as like 1 over t squared. Think about it as a number like that, so small, okay? That actually means that you're only gonna choose, basically at most, one different action over a trajectory of length t than pi is gonna choose, and you can't screw it up too much, okay? That's the kind of basic intuition. This style of algorithm is called conservative policy iteration. Conservative because it sticks to the old thing. That's the heart of it. You don't actually have to do this backup. You could just do it by doing rollouts from a state and estimate the Q function as well, which is the even less dangerous thing to do. Okay, we'll talk about that in a second. What I want to talk about now, we've talked about the kind of problem, we've talked about the kind of solution. By the way, this style of solution, it appears everywhere. This is how almost all modern policy improvement things work. They do it typically in a more subtle way. So they do it in a way that, I forget, one of the two of you were talking about, natural policy gradient kind of things. They do it by having one policy and shifting the parameters of that policy rather than mixing together two policies. But they do the same thing. They promise they won't change the distribution of actions too much. They estimate the key values, promise they won't change the distribution of actions too much.
What is the superscript for the second pi? I can't like see that from here.
Proposed is what I was saying, just it's proposed by the policy improvement operator, and you're not doing what it wants, you're doing something in between what it wants and what you did before. Yep. Good. Okay.
You mentioned alpha is 1 by t square rather than 1 by t. Is that because if we take 1 by t, it will converge to pi proposal via some Liar Robin
1 by t is actually the intuitive answer, right? Because then you're only on average changing it. In expectation, you're only changing it one of the time steps, right? I was picking 1 by t squared because that way it's very unlikely you'll ever change 2. Okay? And the proofs that this thing works basically bounds the probability that you choose more than one action wrong. Okay? But intuitively, you want to change one action, so it should be 1 over t. Right? It's just that 1 over t is harder to prove things about because you might choose 2 actions and screw things up more. That's the rough intuition. Yeah.
So if you connect this back to the no regret online learning stuff and stability you were talking about earlier?
Yeah, it's very much, in fact, you can write down versions of this that use no regret algorithms instead of this thing. But it's the same notion, right? I'm doing something which is good, right, on the kind of data set I'm given, but then I'm being stable. I'm not changing things too much. Okay? It's the general lesson in any of these kind of problems that feel slightly adversarial? This feels slightly adversarial because your max operator is exploiting your errors. It's actually like making you look really bad where you make errors. Okay, so if you want to combat that, being stable about your policies is a strategy for that. Okay, let's see. We're going to talk about policy search by dynamic programming. Chalkboard, not chalkboard. I think I can safely erase this one, which is another strategy for doing this. Okay, so. Policy search by dynamic programming. Okay, so the idea here is what we're going to do is we're not going to back up value functions, we're going to back up policies. And so there's this famous quote, so Bellman was the person who invented dynamic programming. He had this famous quote, which is in his book, I guess it's not that famous, but whatever. An optimal policy has the property that whatever the initial decision is, the remaining decisions must then constitute an optimal policy. So what optimal policy is, it doesn't matter how you got to a state. What matters is you act optimally thereafter, right? That's the rough idea. There's no statement of value functions in that, okay? And in fact, value functions are basically just a technique of caching that same concept. It's really a statement about policies. It says if you want to be an optimal policy, you've got some set of time steps t. To be an overall optimal policy, you should be an optimal policy here. So however you get, so think about this dimension is state, and this is time discretely. Okay. You get to some state S. To be optimal, you better be optimal when you arrive at S. Okay? That's the notion. Then, intuitively what we do is we find a policy that's optimal at the last, or near optimal at the last time step. So imagine there's two actions you can choose. You arrive at that state, it chooses the best of the two actions. Okay? You build something that approximates a good policy at this time step. It relies on the fact that you can, again, sample at the last time step, which we've assumed. Okay. Then what I can do is I can fix this policy, call this policy pi t minus 1. I can fix this policy pi t minus 1 and hold it fixed because I know it's an optimal policy or a near optimal policy. Then what I'm going to do is step back in time. And I'm going to totally ignore this Q function nonsense. It's all nonsense, okay? And what I'm gonna do is I am going to try the, again, just think of it in your head as there's two actions because it's easier. The two actions that are available to me, okay? And then what I'm gonna do is I'm gonna execute pi t plus 2 minus 1 because by assumption, it was near optimal. Okay? And it will choose one particular action. And then what I'm going to do is look at the total reward along each of these trajectories, right? No Q function, just the total reward along each of these two trajectories. And I'm going to pick whichever of these two actions is the best. Okay? And then I'm going to learn pi t minus 2. Okay? And then I'm going to just do that inductively. So back here, I'm going to consider the two actions that are available to me. I'm going to execute the policy going forward from those two actions, policy I've already learned at the future time steps. I'm going to compare the total reward of each of those actions, and I'm going to choose the action that is that gets me the biggest total reward. Does that make sense? Okay, no bootstrapping, right? There's no operation where I'm taking a approximation here and magnifying errors, okay? In fact, let's say I do the approximation pi t minus 1, and I'm in this part of the state space, maybe because it's rarely visited how I generate my samples. Maybe up here, I do a bad job. Policy's not good right there. Okay? What will happen? So what would happen in the Q function estimation is the Q value estimate might be high. And then I might think, oh, I should try to go there. right? My samples are thin, but my Q-value function estimate's too high, and I push probability mass there. What happens if I actually look at the full rollout when I execute pi t minus 1? Well, I see that the total reward is low because the policy at this time step chooses some bad action. If I could draw a skull and crossbones, I would. This is some bad action. That's what pi t minus 1 chooses. And so I will know back here that I should not choose this action because it's going to lead me to a place where this policy is bad. So I never bootstrap my errors, right? I never say like, hey, this is a place that looks really good, but only by chance. Okay, does that make sense? Questions about this? So this is a sketch of an algorithm. Try to write it as an actual algorithm. Yes?
So how do you know that the action is bad when you're looking at it from the rollout, but not when you're like learning the IFS?
Imagine this is a place that I didn't sample during learning the pi t minus 1 step. Okay? Take that as the extreme case. I just didn't sample there at all. I got no samples in that area. Okay? The function approximator for let's say, try to Q function approximate, how good is it up there, is going to be totally arbitrary, right? Think about it as totally arbitrary and too high, right? Because that's the bad case. Okay, so if you were to approximate the Q function, it's really high and wrong, okay? And the policy is bad there. Okay, now I draw a sample and it ends up in that spot, right? Because back here I choose to go up. Now I draw a sample, I follow the trajectory, it ends up in a spot where the Q function estimate is bad and high, and the policy is bad. Now I look at the sample return, and the return's bad, because I end up in the dead state, right? I end up in somewhere bad. Does that make sense? It actually forces me to draw a sample there and see what the performance is. Okay, the bad thing about this algorithm, what's the obvious bad thing about this algorithm? It's worse than value iteration. Clearly worse in one way.
You have 2 to the t possibilities to explore.
No, it's not that bad, but it's t squared, right? Because at the last time step, I draw length 1, right? At the second to last time step, I draw length 2. At the third to last time step, I draw length 3, right? Where in value iteration, I'm just going backwards in time and drawing length 1 trajectories, right? So it's t time steps back, on average, think about it as t over 2 is the length of my trajectory, so it's like t squared, right? So it's substantially more expensive. Okay, so it's a t squared algorithm instead of an OT algorithm. The advantage is it's much more stable. That's the intuitive advantage. The key thing, going back to the policy iteration, conservative policy iteration, is we are only changing one time step at a time, right? Just like I said, it's a pretty good idea to only change one time step by these stochastic policies by making it so that it's unlikely you choose more than one time step to change. Here we're forcing the algorithm to change one time step at a time. Okay, good. If we turn this into a practical classification algorithm, I wonder if I should do it as classification or regression. Let's do it by regression. Okay. H, T, -1, 0. Okay. For each state in our sample set, I'm going to do the version where we try both of the actions that are available to us. For each A, although you could just draw these at random too. Because I'm doing, in our set A, I'm doing the regression. Okay. Get a sample, which is the sum of the future rewards. So the target is sum of future rewards executing. We are at pi t plus 1, pi t plus 2 that are already learned. Does that make sense? Up to pi t minus 1. Okay. That's gonna be the target data point that we're going to use. Okay, and then we're going to have a regression data set that looks like SI, A, I'll call it AJ, these guys, AJ, and then this target value, target IJ. Okay, you get a data set that looks like this, for all I, for all J. Okay. States from our sample set of states. Okay. So SI for SI in some sample set of states. So a data set of states. Okay, and I am going to then learn this Q hat thing. Is regress this data set, DI, regress on DI, DT, rather, data set. So I've drawn my favorite regression algorithm, least squares regression, let's say, on this thing. Okay, and then pi t is just okay, the only thing that I'm doing different is I'm actually executing these future policies. Executing them, getting traces and seeing how well they do. Yep.
Does this have any guarantees towards finding the most optimal policy?
For what, I'm sorry?
I imagine the top line in the graph you drew, it's possible that the optimal policy goes up and then down, right? So there's some value in the intermediate states, but you would never find it because the final state will kill you, basically.
Because I do a bad thing out here.
Yeah, so maybe
Yeah.
the first actions were, like the intermediate reward was.
Yeah. So the guarantee that this is gonna have, I'll give you the flavor of the guarantee that this is gonna have. Okay, I gotta tell you how these SIs are generated, right? Because by assumption, I didn't generate samples out here, and so I'm bad out here, right? The guarantee that this is gonna have, I will write down because we don't have time. I was really hoping to go explain to you the performance difference lemma, which is the key to proving this thing. So the guarantee this is gonna have is V pi S0, the initial state, of the policy I learned this way is greater than or equal to V pi reference, any reference policy I would like to compare myself against of S0. So how much total value you get from S0 minus epsilon mu plus d I ref times step t equal mu infinity 1 t. Okay, let me explain what each of these terms are, and this will answer your question, I think. Okay. Policy you learn is compare yourself to any policy you'd like. Okay? And then you will do as well as that policy minus a combination of two things. One, a term that relates to how well you do this regression problem. Okay, so if you do a bad job on the regression problem, you got big problems. Okay. How well you do on the regression problem, and then this term. So what this term means is I have to sample these states from some distribution. Okay. What I would like that distribution to do is cover everywhere the policies that I want to compare against go. Okay? Think of this as max over all states, the ratio of d pi ref t of that state versus how I sample those states. So if I sample space in a way that does a reasonable job as a distribution that's close to some good policy, may not be the optimal policy, but some good policy, meaning that it's never the case that the sampling distribution is really low, but the policy that I want to compare against goes there a lot. Okay, that never happens. And I do a good job of regression. Then I must do a good job overall. The case you're kind of describing is I'm bad at some place, but there was a good policy that would have gone there, right? I didn't actually draw samples there. I can't make a good comparison against that. Okay. This idea, we have to stop there, unfortunately. This idea is called a baseline distribution. So it is a set of states that's telling me, it's giving me a really important piece of information. Where is it important to focus my energy on getting things like approximations correct? Great places for this, expert demonstration. Experts can show you where good policies spend time. Right? Any initial policy you'd like to start from that's decent will show you where good policies spend time. The key thing to notice is you really want it to be that you cover the good policy. It would be better to be more noisy and more random rather than too tight. Because if you're too tight in your distribution, you might not learn how to do things that you need to do.